let's talk in a little bit more focused way about evaluating separations. So we want to talk about separation efficiency or column resolution. We want to talk about reasons why bands might spread, and then we also want to talk about reasons why you might end up with an asymmetrical peak shape. And so these are the kind of things that you want to be thinking about whenever you're doing chromatography, and you just want to be aware that there could be problems and where they might be coming from if you do encounter them. All right, so let's talk about a chromatographic peak. Ideally, you should have a Gaussian-shaped peak where you can say that the total height is h. You can also look at the half height, so that's half of the y-axis. And if you take the width at that half height, then you would have something called the full width at half max. So FWHM. And so in your book they call it W half or W sub half. But that's an important point that we're going to need. In the rest of the discussion. So let's talk about resolution. How do you figure out if you have adequately resolved two peaks? Well, if you're trying to resolve two peaks, you need to look. You can look at if they overlap. And the way that you do this mathematically is with the equation 0.589 times the difference in the retention times divided by the average width of the peaks. So you can calculate that from the full width half max. And for a good quantitative separation, you're going to be looking for a resolution of greater than 1.5. Alright, so one of the reasons that peaks broaden is due to diffusion. And diffusion is essentially the net transport of particles from high to low concentration. So from your injection to the solvent surrounding it where there's less concentration. And that's as a result of Brownian motion. There's really nothing you can do about it. But it's related to retention time. The longer things have to, diffuse around, then the broader your band is going to be. So the bandwidth is proportional to the square root of the retention time. So if the retention time is increased by 4x, then your peak width is going to increase by 2x. You can also think about your column in terms of a theoretical plate height. And the distance of one plate, or that one plate is defined as the distance that your solute and solvent would travel, over which you would have one period for equilibration between the stationary and mobile phase. So sort of this is theoretical, but you can calculate it. So you calculate it. Actually, what you calculate is the number of plates. So the number of plates n equals 5.55 times the square of the retention time divided by the full width half max squared. You can also think about that in terms of resolution, which is the square root of the number of plates divided by 4 times gamma minus 1, where gamma is the ratio of 2 retention times. Alright, so there's a couple more things that can go right. You can have broadening during injection, like if you don't get it all in all at the same time, like there's some finite amount of time that you are depressing the plunger on your syringe, or the injector is sucking up and injecting solution. And you can also have that during detection. So it doesn't always necessarily happen in the column. We've talked about longitudinal diffusion, where you have diffusion through your sort of along your column because of the Brownian motion. You could also have issues with if there's a finite equilibration time. If equilibration, we think of it for chromatography as being an instant process, like you are instantly on or off the stationary phase. But there's a time associated with that. And you can also have multiple flow paths that can broaden peaks, because if you take, the most direct route possible, you're going to get there faster than if you take the scenic route through the column. you know, molecules don't know the most direct or the most scenic route through the column, but they do take different paths, and depending on how many different paths they take, then it takes some different amount of time. And there's good pictures of this in your book or other places. Oh, okay. So another thing that you want to think about for when you are if you're looking at an asymmetrical peak is the idea of fronting, which is where you have a bunch of where you have the front end of your peak it doesn't look Gaussian, it looks asymmetrical, or tailing, where the back end of your peak sort of tails off and isn't symmetrical. So fronting has to do with if you overload your column. So if you put a bunch of solute in there and it's all moving through, and some of the solutes are having the normal interactions with the stationary phase, but some of them are like stuck in the middle. It's like being stuck in a crowd, and they're just getting pushed through without having the opportunity to interact with the stationary phase as frequently. And so when that happens, you would have potentially some portion, you know, the portion of the solute that didn't interact as many times with the stationary phase, it's going to start to come out first because it didn't have time for those interactions, and then you'll eventually so it smears out your peak and broadens your peak, but mostly on the front end. For tailing, it's because there's differences in the strength of the interactions that your solute can have with the stationary phase. And so if you have, but only there's a small number, basically there's a lot of weak adsorption sites, and there's just a few like really strong adsorption sites. And so if a solute comes in and gets stuck in one of those strong adsorption sites, it takes it much longer to get away. Whereas, you know, the rest of the adsorption sites are like, oh hey, sorbed, desorbed. Okay, I'm traveling down the column, sorbed, desorbed. If you get stuck in one of these things where you're sorbed, it takes it longer to desorb because the interaction is stronger. So that's what can happen when you have tailing. So if you think about this as far as the concentration in the mobile phase versus the concentration in the stationary phase, and where this K equals, let's see, Cs over Cm. And it should be constant if you aren't having any trouble with your tailing, or you shouldn't have any difference in this ratio if you have normal chromatography. But if you have K that decreases as a function of concentration or increases as a function of concentration, then you really need to be looking for either fronting or tailing.